Okay. So, if you're watching on YouTube, we haven't gone too far. This is the first slide. So yeah, by learning about compilers, you'll become more skilled at writing effective code and debugging when things go wrong. But we won't have the time to actually write a full compiler together. But this should be a good starting point for anyone who actually does want to write one. So these are the stages of a compiler. So first we start with a character string, which is the program in the language that you're trying to translate. And this gets fed into the scanner portion, which turns it into tokens. And these tokens are fed into the parser, which simultaneously validates the structure of the program. Like, for example, if you're missing an if, it's going to tell you. And it also generates what's called an abstract syntax tree, which describes the structure of the program. And after that, the compiler just does some semantic routines on the abstract syntax tree, like making sure you're not assigning a string to a Boolean variable or something. And after that, it does some optimization, and it then spits out some assembly code in the code generation step. And on the bottom here, you can see how a compiler might compile this line into x is equal to 5. So in the scanning step, this is broken down into the identifier token equals the 5 token and the semicolon token. And after the parsing step, it's broken down into this abstract syntax tree. And there isn't really much to do in terms of optimization. So the compiler can then just spit out the assembly code xdb5. And what this means is just the assignment of a byte containing the value 5 into a location called x. So yeah, any questions so far? Area db is a command to move a byte containing the value 5 into a named location called x. Okay, doesn't seem like anyone has any questions. Okay, moving on to scanning. So these are the categories of tokens that most compilers use. We have keywords like if, else, while, do, try, catch, and we have identifiers, which are variable names. But if you know object-oriented programming, these are also class names and object names. I think strings and numbers should be self-explanatory. Comments are supposed to be ignored by the compiler, but in some languages, like Python, indentation in white space is actually part of the syntax. Like in Python, indentation is a substitute for brackets. So with that, let's go over this naive approach to scanning. So first, we'll read one character at a time, and if there's nothing else after it, assign it the proper token. But if else, keep reading. So it turns out that this is actually really inefficient. What do you guys think would be a better approach to scanning? Any ideas? Here, you're kind of close-ish. Yeah, Jordan is closer. Viha, I'm not sure what you mean by that. Okay. So the actual approach that most compilers use for the scanning step is regular expressions. So instead of going character by character, we can evaluate entire tokens at once using what's called regular expressions, which are strings that define a search pattern or language. So as an example, the regular expression hellos defines the language hellos. And what this means is that only the string hellos would be matched by the regular expression. For the second regular expression, the syntax just means that you can choose between either W or O when you evaluate a string. And that means that either is valid. So this will generate the language wow and woo. Sorry about the background noise if you can hear it. So this means that either wow or woo would be matched to this regular expression. And for the third regular expression, MO, O star, this star operator just denotes that we can repeat whatever's in the parentheses as many times as we want, and it's still going to match the string that we input. So as you might expect, this generates the language MO with 1 O, MO with 2 O's, MO with 3 O's, and so on. And finally, this syntax just means that we can choose any character within this range, and it's still going to match. And this generates the language A through X. And if we change this X to Z, it would generate the language A through Z. And side note, regular expressions are actually used really often in software development to match strings of all kinds. It's not limited to just matching tokens. So does anyone have any questions about this? Regular expressions? No, unless like you can add a lot of O's and it would just take a long time to parse through it. Does that clear up your question? Yeah, Jordan, O star would be different because the first the first element in this set would be invalid because it's only matching yeah it's only matching multiples of 2 O's, so this wouldn't work, and and I think the third one would also not work. Yeah. Okay. Okay, so now that we know what regular expressions are, let's informally define identifiers like variable names as a sequence of letters and numbers, but a number must not come first. And this is true for most programming languages. So it turns out that this informal definition maps to this regular expression, A through Z plus either a character in this range or a number in this range, repeated as many times as we want. And and we're going to see how this works on this website, Regex 101. Here we can write regular expressions and test them here. So let's just write A through Z plus either character in the range A through Z or a number between 0 to 9, repeated as many times as we want. So here we can test our strings. We see that X is a full match, X is a full match, IHS is a full match, IHS 76 is a full match, But notice that 76 IHS isn't a full match because it starts with two numbers. So yeah, if you want to learn more about regular expressions, I encourage you guys to play around with this website. Down in the bottom right, you can see all of the types of tokens you can put into your regular expressions. And yeah. So it turns out that any regular expression can be turned into a deterministic finite automata, and that DFAs are actually really efficient in terms of software and hardware. So the way we would do it is we would apply what's called Thompson's construction to a regular expression, and that'll turn it into a non-deterministic finite automata. And as a refresher, with an NFA, if you're given a state and a character, it can move into more than one state. And yeah, and we can apply subset construction to this NFA to get a DFA. I'm not actually going to go over what these two are, but if you're curious, I highly encourage you to look these up. So as an example, this is the DFA for the regular expression MO star. So if we read in an M, oh, by the way, as a refresher, a circle around a node indicates that it's in an accepting state, and this indicates that this is the starting state. So if you read in an M at the starting state, we move to this node states, and if we read in an O, we move into the accepting states. And notice that this self loop is how this is translated. So we could read in as many O's as we want, and we'd still be in the accepting state. But if we read in an M, we move to this rejecting state. And the same goes for if we read in an O at the beginning or an M after the first M. After it reaches this state, it just loops back for any valid character. Any questions? Okay. Yeah, it's just a DFA representation of the regular expression. Implementations of scanners do this because it's just more efficient. So in practice, people actually use what's called scanner generators to generate scanning programs, given a set of regular expressions and tokens. The Flex scanner generator, which is compatible with either C or C++, was one of the earliest scanner generators, and it's still widely used today. But you can also use simpler libraries like the Ply module for Python, which does both scanning and parsing. And I think we have enough time, so let's try implementing a simple scanner in Python. I'm going to use REPL, but feel free to use whatever IDE you want. I think I'll just give a minute or two for you guys to get an IDE open. Let me know when you guys are ready. Okay, I think that's everyone, question mark. Okay, so first we're going to install fly using pip. And after that, oh, by the way, what we're doing here is implementing a simple scanner that scans and tokenizes mathematical expressions like 5 plus 4 or 5 plus 4 times 5 or something. So first we'll import the lexa module of apply under the alias lex. Then we'll write this line. So this is what builds the lexer. It's just what they call a scanner. And we're going to add a few definitions before this line, because what this line does is check for what our token names are and what we should do when we hit certain tokens. So we're going to define a tuple, which is like a list that you can't modify, of our token names. Can someone send an apostrophe? I think he isn't working again. Thanks. Okay, so our possible tokens are number, plus, minus, times, divide, left parentheses, and right parentheses. I'll give you guys a few seconds to finish copying that. Okay, so now what we're going to do is define a few regex rules for our tokens. So as I said earlier, this line is going to look for these definitions. So we're going to define our plus token as this, and it'll just look for this symbol. And by the way, you should prefix the letter R to make it a raw string, because in most languages, the backslash character is an escape character, and what this R does is prevent the backslash character from escaping whatever's after it. And we're going to do a similar thing for the rest of the tokens. By the way, we're not going to do that for the divide symbol. Left parentheses, right parentheses, and that's all the tokens except for the number token. For the number token, we're going to define a function that tells the scanner what to do with numbers. So def t number takes in t, which I think is a token object. And we're going to write a regular expression at the beginning of the function. And this is just going to ensure that we match a number. And so what we're going to do is convert the value of the token into an int. And after we do that, we can just return the token object. And after we finish that, we're going to define a function to count new lines and track line numbers. And similarly, we're going to define a regular expression to detect new line characters. And after we do that, we're going to increment our count for line numbers. Yeah, and that's correct. And after this, we're going to define the characters what we should do in case we encounter spaces or tabs, which this regular expression should detect. And finally, we're going to define an error handling rule. T error takes in a token object, print something like legal character or something, and skip the current line. I mean, skip the current token. I think that's everything it needs to define. I'll keep this up for a few seconds in case you miss something. Okay. So after this, oh, sorry. Sure, Harry. If you run, nothing happens. Because we haven't done anything with the scanner yet. Jordan, in Python, you can use either double or single quotes for strings. You can do whichever. Harry, you don't have to, but you can if you want to. Where, Jordan? Skip. This is a one. Is everyone ready to continue? Okay. So this line builds the lexer or scanner. Here, you don't need to clear the shell. So after this, we can just define a variable containing what we want to feed into the scanner. So just give me a mathematical expression, anything like 5 plus 4. This doesn't support powers. 10 divided by 2 should work. Okay, so we're going to then input our data using the input method. And plus 2 plus 2 minus 1. Okay, so we're going to import our data using the input method and use this loop to tokenize. So while this is true, we're going to grab the current token and check whether if it's a token. If it's not a token, break out of the loop. But if it is, then print the token. And if we run this, we can see that it correctly parsed everything. So notice that it just ignores spaces. So if I did this, it wouldn't matter because it uses regular expressions to match things. So yeah, feel free to play around with this data string and test your own expressions. So yeah, give me a second. That's very cool. Okay. Yeah, I'll upload this code after this meeting. Okay. So let's move on to parsing. So int x is equal to 5 is a valid statement, but x5 is equal to int is not. So the way we validate the structure of tokenized programs is by using what's called grammars. Before we get to grammars, here's some terminology. So terminals are tokens, and non-terminals are the structure of a program. And I'll get to what this means you'll see what this means in a bit. Sentences are valid sequences of terminals, and sentential forms are valid sequences of terminals and non-terminals. So with that in mind, we have the following example grammar. And to illustrate this, I'm going to use an example expression. So let's say we have the expression 7 plus 6. So this P non-terminal represents an entire program. And what this says is that a program can map to an expression non-terminal. So first we'd say that this is our time program, and we'd use the grammar rule to map it to an expression. From there, we can pick from the last 3 rules, and we can see that the second rule makes the most sense because we have these two separated by this plus sign. So we then parse it like this. And for each of these e's, we can then apply the last 2 rules. Neither of them are an identifier, so we can ignore the third rule. So this means that we should use the fourth rule to parse number 7. And we can do the same thing for 6. And yeah, that's how you use a grammar to parse an expression with this grammar. Any questions about grammars? Okay. Um, so like scanners, parsers can also be generated using what's called parser generators like GNU Bison, since writing parsers by hand is inefficient. And um, these, these parsers use what's called parse tables to sequentially read through tokens and either validate the tokenized program or generate an abstract syntax tree. So here's the parse table for the grammar from the previous slide. And I think you guys can see how the grammar from the previous slide maps to this parse table. Given a non-terminal p, we map to the other non-terminal e. But if there isn't, then we follow to the end of the program. And a similar thing happens here. For each expression, we can read an identifier or an int. And afterwards, we can either declare that the program has ended, or keep following through the plus token. So do you guys want to do another example, or does this make sense? Okay. So also, side note, this actually isn't the exact type of parse table used by parser generators, but it's kind of close. So after we parse through our tokenized program, we can generate what's called abstract syntax trees, which describe the structure of our program. So for statements, we can just read through and add to the tree as follows. So we read in the while, make that the root of the tree, and then parse through whatever's in the parentheses, and then parse through whatever's in the brackets as follows. And a similar thing happens for expressions. We parse from left to right. So 56 times, and because this is in parentheses, we go down a level. The result of dividing 7 and 2. And you saw this, I think you guys saw this earlier, but this is how declarations are parsed. We go left to right. So y is equal to 0. And notice that we don't assign the int anywhere. That's for the semantic analysis step. So yeah, this is how abstract syntax trees are created. I think we have time to go to type systems. Okay, let's do that. So moving on to semantic analysis, or in other words, checking whether or not you try to do something illegal with the type system. So all languages have what's called a type system that defines what the types of variables and classes are. Sorry, not classes, just variables. So this defines what the various types that can be assigned to variables and functions. And it serves several purposes. It allows for checking for correctness, like you can't assign a Boolean to a floating point variable unless you did some implicit conversion, but that's not present in most languages. And it also helps with performance. Like instead of storing some constant value as a variable, you can load it into a register. And finally, you can define an implicit type conversion system to not have to convert a variable to a string every time you want to print it. Like in Python, you can just print 1 or 76 without converting it into a string first. Any questions about this? Okay. So type checking is a major component of semantic analysis. We're not going to actually go over it because it's actually a really complex part of a compiler, but we'll just go over why compilers do it. So compilers do it to determine what names or identifiers map to what values in memory. They do it to catch type errors at compile time rather than runtime. And they do it to stop programs from doing undefined things. Like if you guys have experience with C or C++, you'll be familiar with undefined behavior. Rewriting some random block of memory when you're actually just trying to work with an array by going out of bounds with your assignment. So yeah. I don't think we have time for the rest. Okay. So next week we're just going to be doing code generation, and in the second half we'll be doing hackathon judging. So if you have a project to submit, reminder to submit it a few days before. I'm going to probably open the hackathon to submissions by Thursday or something. And yeah, thanks for coming.